Okay. Good thing you're here because out of all of them, this is probably one of the more important lessons because everything is new. um, because everything we've done up to this point, we've used the Z table, we've had the standard deviation, and those things. If we don't have the standard deviation, we can't use the Z table. So we have to use something known as the T table. So that's what we're going to start looking at today. So the equation that we have right here looks very similar to the z-score. So it's the sample mean minus the mean of the population divided by the standard deviation. But that S is no longer, so the S is the standard deviation of the sample. Since we don't have the standard deviation of the population, we could take the standard deviation of the sample that we have. Divided by the square root of the sample size. That hasn't changed. The one other piece that we're going to have is known as degrees of freedom. You typically will see this abbreviated as DF. Degrees of freedom is specific to the t-table, and it is always one less than your sample size. So it's n minus 1. So if I had a sample size of 25, my degrees of freedom would be 24. Always one less than your sample size. All right. All right, we're going to use it in a second. So basically, what your T score does is it kind of squishes the normal curve. All right. So a degrees of freedom of 1 will be there. As the degrees of freedom gets higher and higher, it basically becomes very similar to the normal curve. Which number do you think ends up being just like the normal curve? What's the number that keeps coming up? What's the size that keeps coming up? 30. A degrees of freedom of 30 typically gets pretty close to a normal curve. However,
what was your question that you asked?
Like, what's the number that keeps coming up on sample? Like, what's the number that normal becomes a normal curve?
Oh, okay. So it's 30.
It's 30, yeah. So in this case, we still can't use the z-score and the normal curve at that point because we don't have the standard deviation, but the curve is very similar to it at that point. All right. But good guess with the 6.5 and 7. Yes, it was getting closer as it got to 6. I can see where that came from. All right, same concepts of the z-score or the z-curve as the t-curve. Total area under the curve is 1. It extends indefinitely in both directions, but never actually touching 0. It is symmetric about the 0, so you still have the negatives and the positives. As the number of degrees of freedom becomes larger, t-curves become increasingly looking like the normal standard curve, which we've just mentioned. So very similar in respect to the z-curve. It's just things that we have to tell so you know those things exist. So nothing crazy there. All right. So let's look at a problem using the t-table so we can actually see how it's done. So you're going to see it says for a t-curve with 13 degrees of freedom, determine t of 0.05. So remember that 0.05 is always looking at to the right. Okay. So we're looking at the value of this piece over here. So we are going to go to our t-table. So this is what our t-table looks like. You should have a very similar one in your book. It should look similar to what I have on the screen, I think. Let me see what yours look like. I just want to see. Yeah, looks like this. All right. So 0.05, 13.
1.6.
Okay.
That's right.
All right, so that's one tail. Okay, that's fine. I needed to know if it was one tail or two tail. Okay. Yeah. So, all right. So if you notice the one, so what I also did is on my website, I linked this. So if you want to use the same one on this website, you can click on this one. So yours in the book only has the one tail, which is fine. Because depending on when we're looking at it, remember, like in the Z tables we're looking at 95%, that's 5 on both sides. So that would be a two tail or one tail. So we have to keep that in mind. Your book is one tail, so you would just cut it in half for the two tails. So we're looking at 0.05. So we're looking at this column right here. And we're looking at, it says a degrees of freedom of 13. So they already gave me my degrees of freedom, so we do not have to actually do the calculations for that. So we're going to go down to 13. And we're going to go over to the 0.05, and we're going to get 1.771. And that is the t-score for that value. Okay? So once we get the t-score, that's just like, we can use that just like a z-score. That's how many standard deviations we are away from the mean. So once we have that score, everything else that we've been doing with the z stuff still applies. All right. When you get out your book, or if you don't have your book, you want to find a t-table because we're going to be using that. That's the only thing you've missed so far. All right. So actually, make this a little bigger. This is just like we had our procedure for our Z. When we're looking for confidence interval, this is our procedure for the t-table. So my assumptions are still pretty much the same. I need to have a simple random sample. I need to have a normal population or a large sample. Again, that large sample comes down to 30. Anything over 30, we can assume is normal. If it is under 30, we have to figure out if it's a normal population. And you're going to see that quite a lot more often in the T's than you would with the other stuff. So I linked on my website, and I'm actually going to show you a site that actually will allow you to figure out if it's a normal curve or not. So you won't have to actually do that out by hand. And in this case, my standard deviation is unknown. So for a confidence level of 1 minus A, that's how we get that 0.05 or 0.01, whatever one we have. We're going to use the t-table, which is what we did, with a degrees of freedom of 1 less than the sample size. My confidence interval, this is just, the only difference in this is it's t instead of z. And it's the standard deviation of the sample instead of the standard deviation of the population. So you'll notice that this formula looks almost the same, just with a couple symbols changed. Okay. And then we could figure out our confidence interval for those. Any questions with that? Let me know when you guys got it. Just putting commas in my list of values here. All right. Let's actually do a problem. Okay. So this is losses for a sample of 25 pickpocketing offenses. So this is what somebody's pickpocketed. How many values do I have there? I have 25. Is that above 30? No.
That's less
Okay,
than 30.
that is less than 30. So we have to determine if it's normally distributed. Okay, so a couple things we have to do now. First thing we have to do is we still need to figure out our mean and standard deviation. So we can still use what we did before. Calculator.net does that fine. The only difference in what you're going to do here is it is a sample. So there's the two buttons, population and sample. Make sure you choose sample. Okay. So it does change the formula slightly, change the standard deviation slightly. So in this case, I have a mean of 513. So my mean is 513. And we always go one more place than what they gave me. So in this problem, there's no decimal places. So we'll go 513.3. And my standard deviation is 262.2. Okay, so always go one more decimal place than what you have in the problem. So since this problem has no decimal places, we go one decimal place. All right, so that's for my standard deviation. And if you go back, you can see here, see how it says population and sample. Just make sure you put sample. The next thing we have to figure out is it normally distributed? So I've linked this on my site. This is just going to give you a nice little curve. The thing with this is what it's basically, I should share that actual tab. So we're going to put this stuff in, and then it's going to give you a curve. What it's doing is it's literally finding out how many standard deviations every point is away from the mean. Okay? So what you want is pretty much a straight line. Okay? You want your data to be pretty much on a straight line. Nothing crazy. All right? So the closer it is to a straight line, the more likely it is normally distributed. Okay? So in this case, this one is pretty close to that straight line. All right? So we can claim this one is normally distributed. And you can look down here at the correlation. If that's over 0.95, we're good. Okay. All right. So this one, normally distributed. So we're going to be able to do our, and they gave me the graph, so I'm not going to use that one. So we can actually go through and do this problem, the steps now. Okay. All right. So we've got our standard deviation and our mean. So we've got those values. We know it's normally distributed. So we can do this. Next thing I want to find is my t-score for this. So we're going to do, close the tab that I did not want to close. So for this one, we're going to do 95% is going to be my confidence level. So when I'm looking at my t, what's the number I'm putting down here? What's the number I'm looking? If I'm looking for 95%, so 95% is T of what? 0 what? Almost. Almost. Yeah, you're getting worse. Right. It's 0.25. Why? They're on both ends. So we're looking at 0.025. Okay. So because I want, it's now in essence two-tailed. Okay. The first one we were looking at was just one side. So it's just that one. This, since we're going in both directions, it's two-tailed. So we've got to keep that in mind. Yes. So if it's going to be a one tail, it'll typically tell you, but a lot of times you can tell from the problem. So like if we're looking for a confidence interval, we're obviously going both directions, right? So that's where the two-tailed comes into play. Next week when we get into chapter 9 and we're starting to look at those things, you're gonna start to see that a lot more often, where it's like, okay, I don't care about the negative side. I really just care about that one side there. So I'm just looking at that end. Okay, so it really depends on what the question is, and we're going to start to look at how to figure that stuff out. For today, most of the cases that we're looking at confidence intervals. It's going to be two tails because we're looking for both directions. All right, so I'm looking for that. And what's my degrees of freedom for this problem?
Degrees of freedom is going to be 24.
Correct, because it's one less than my sample. My sample is 25, so I'm going to be looking at 24 in this case.
So n minus 1, with n being 25, correct?
Yes.
That's how we got to 24.
Yep.
Yes.
All right, so we're going to go back to my T-table. And we're looking at 24. And notice how like mine has the one tail and two tail. It does it for me. See how the two tail is the 0.05, the one tail is the 0.025. It's the same column. On yours, you just have the one tail, so you'll have to look for the 0.25 or 0.025, sorry. So we're going to look here, and we're going to go down to 24, and we get 2.064. All right. Everybody figure out how to get the 2.064? Okay. Okay. So we've got all our information. Now I can figure out my confidence interval. So remember the confidence interval is the x, the sample mean, plus or minus, in this case, the t-score, times standard deviation divided by the square root of n. So I have 513.3 plus or minus 2.064 times 262.2 divided by the square root of 25. You can use Desmos for this. 13.3 plus 2.064. So we use Desmos, and you can just do that. And then I know on your phone you can't copy and paste, but I can. So we get our range is 405.1 to 621.5.
The book, they have it round.
I know they went to 2 decimal places. It's fine. Because it's money, so they went to 2 decimal places. So it's not a big deal. So 405. To 621. What was it? 07. I'll write it to 2 decimal places just because it's money. All right. So we are 95% confident that it's between those two. Okay. All right. Any questions with this? Does that make sense? This process?
A lot of steps.
It is. And unfortunately, as we go, the more steps you have. Because you're trying to figure out more things. So like, because when you're looking at data, a lot of times you're not going to have all the answers. You're not going to have all the information. If you have all the information, then you don't need to do it. Somebody's already done it. And that's really the difference between the Z-score, what we were doing in the T-table. It's like the Z-score, somebody's already done all this and figured out the population standard deviation. So if we have that, great. But then I'm literally just using it to compare and make sure my data makes sense. In this situation, we don't have all that information, so we've got to do a little bit more work to figure this stuff out. The other thing is that when you're doing this, because we have to calculate out the sample standard deviation and stuff like that, you typically don't have as many numbers and examples in the book because they're not going to make you do it for 50 to 100 numbers, which means we have to add in that extra step of figuring out, is it normal? And we're going to see a couple examples that we're going to look at now in the next 2 examples of why that is important. So, all right, chicken consumption. So we have to figure out. Does anyone remember the chicken price spike? It was like a year or so ago. The chicken price like went through the roof. Well, that's actually why we have the egg shortage. So the first one happened like after COVID and everything else because like a lot of the factories and stuff shut down and things like that and stuff. So it's like the chickens, like but no, the avian flu is what caused the egg prices to spike. But yeah, very similar thing. So it's important for us to know on average how much people eat of a variety of different things. So this way we can make sure that our production is in line with that. So it shows a year's chicken consumption in pounds for 17 randomly selected people. We want to find a 90% confidence interval for this year's mean chicken consumption. So here is the amount of pounds of chicken that people eat on average over the course of a year. They did it for 17 randomly selected people. Okay, so we have our sample years of chicken there. So before I go through and do the standard deviation and the mean, let's see if this is normally distributed. So if I put all my numbers in there, I get this. Okay? What do you notice? We have an outlier. So exactly. So and that 1 point seems to be making this not as normally distributed as possible. So I can't do it the way that my data is showing right now. However, if I'm looking at how much on average people eat of chicken, do I care if you don't eat it? So in this case, if we remove that option, we say, okay, we're looking at people who do consume chicken. Okay, so if we remove that, so we can go back up here and just remove that one and recalculate. Yeah, now it works. Okay, but how many samples do I have now? I have 16. I do not have 17. So when we do my calculations, I'm now working on 16, not 17. Okay, so go back over here. So we're going to eliminate that value. And my n is now 16. So now we can go to find out my standard deviation. So I'll switch over to the slide as soon as I finish typing my numbers in. Because I can't copy and paste from the other thing because it doesn't have commas in it, and this site wants commas. Happened in the last one I did. So we have numbers put in, we have a sample, calculate. Make sure your count comes out right, it's still 16. So we've typed them all in there. My standard deviation is 11.1, and my mean is 67.1. So my n is 16. My mean was 67.1 or 61? 67.1. Standard deviation is 11.1. Okay. All right, so we've got those values down. In this case, I'm looking for a 90% confidence level. So my T is going to be what? 0.05. And my degrees of freedom is 15. Remember, we still have to take one away from my sample. So we go back to our T table. In this case, I'm looking at the 0.05. And we're going down to 15. And we have 1.753. Okay, so this is what I have. So we can go back to Desmos and plug these numbers in, do my calculation. So we're going to do our mean minus the T times the standard deviation divided by the square root of my sample size, which in this case is 16. Yes. No, it's not degrees of freedom. In this case, it is the sample. The sample size was still 16. My degrees of freedom is one less than that, so it's 15. Good question. So in this case, I have between 62.2 and I'm 90% confident that the average American eats between 62.2 pounds of chicken and 71.9 or 72 pounds of chicken, if we're rounding correctly. And just like in the Z-score, if we increased my confidence, so in this case, I was at 90% confident. If I went up to 95% confident, my T-score goes up. It's now 2.131, which means that my variation or my error in each direction would be greater because I'm more confident that it's going to be between this, but I have a larger range. All right. Before I go on to those. Let's look at this data. So these are adjusted gross incomes in thousands of dollars. So the IRS looked at 12 sample returns, and they want us to find the confidence level for this data. So we've got our data here. First thing, it's less than 30, so we have to figure out that it's normally distributed. So if we look at this one here, this one, we put the data in, and that's what we get. Is that normally distributed? No, it's levels out and kind of shoots up. So does not look normally distributed in this situation. Their actual graph is a little nicer. They do it the opposite direction as this graph does. It's a little easier to see. So you can see how it goes up and then it kind of like levels off as it's going out. Not a straight line. It's not linear. So therefore, this data is not normally distributed. So now let's look at it. Do I have an outlier like I did in my last one that I can kind of remove and it would kind of fix this problem? Not really. It's kind of as is. Okay, so based on what we know, we can't do our t-test for this one. Okay, and from what you know, you can't do it. There's more complicated ways to do it in this situation. Honestly, the best way to do it would be to get more data. All right, instead of getting 12, let's get 15 or 30 or 40 or 50. values. We have the data. Let's pull some more. All right. The last thing, margin of error. Yes,
That's a question on a test, and the answer just we can't.
it won't come up on a question on the test. All the ones that you're going to be able to do. It might be like we did here with this one, where there's an outlier that you're going to have to remove. That's possible. But they will all be ones that you could actually do. So, all right. Last piece, margin of error. Margin of error for the T. Remember, margin of error for the Z was just. So let's go back here. I'll show this. Is just looking at the piece that you're adding. So if you get rid of the mean, so we're looking at how much it varies. So if we were to get rid of the mean, my margin of error is plus or minus 4.9 times. Okay, that's how I figured out the margin of error. So it's just the t times the standard deviation divided by the square root of the sample. It's no different than we did for the Z one. We just eliminated the mean. Same concept for the margin of error. So in this case, that would be my margin of error. It's the plus or minus piece. So if you were looking for margin of error, that would be your margin of error. All right. The last thing we're going to do with chapter 8 is we've talked about two different tests. The key thing now is figuring out what you're going to do when. Okay. So we have our Z-scores and we have our T-tables. We have different assumptions for each one of them. Which one are you going to use based on the data that you have? Okay. So let's look at this first problem. All right. So we have millionaires. So we have 36 randomly selected U.S. millionaires for those years. Based on this, is it a simple random sample? Yes, they randomly selected. Is it normally distributed? Yes, we've got 36 of them. We're going to assume it's normally distributed. Okay, so what do I now need to know to determine which test I need to use? Nope, before confidence interval. What's the difference between the Z-test and the T-test? What's the one thing that I need to, what's the one difference between the two and the assumptions?
In the Z-test, the standard deviation has already been given to us.
Right.
Whereas with the T-test, you have to figure it out on your own.
Correct. So do I have the standard deviation or do I not have the standard deviation? That's the question. If I have the standard deviation, I can use Z. If I don't, I have to use T. Okay. In this problem, if I go back and unshrink it, they gave us the standard deviation. Okay. They told us the standard deviation of ages of all U.S. millionaires is 13 years. Okay. So we have our standard deviation. So that means I can use my Z-table. Okay. So we want a 95% confidence interval for this. All right. So take 5 minutes or so and start. And they did the mean for you already. So my sample mean is 58.53, and my standard deviation is 13. So you do not have to figure out your sample mean. They already did it for you. What's the z-score I'm using for this one? If we're doing 95%?
Positive or negative 1.96. Positive and negative 1.96.
Yes.
Because the A is 0.95.
Yep.
So you subtract the 0.95 to get 0.05.
Yep.
Then
Then
that correlates to the z-score that I just said.
we got to cut that in half. Remember?
Okay, so that's cut that in half, which will be 0.025.
Right. Which is the 1.96. That's also the z-score that I told you. Remember, I gave you the z-score for 90%, 95, and we did. I think I gave you 99 too. So, because those are the three that commonly come out. So my mean is 58.53. He is 1.96. That's 13. And my n is 36. All right. So you should have gotten that. So 54.3 is my lower, 62.8 is my upper, and the error is 4.2. Remember, you're basically doing your mean minus the z-score times the standard deviation divided by the square root of that. Okay. So I'm 95% confidence that the mean age of millionaires is between 54.2 and 62.8 years old. All right. Next one. Diamond prices. So I have a simple random sample of 18 1.5 carat diamonds. Okay. It's a random sample. They told me that. Great. Is it normally distributed? I don't know, right? So I have to find out. So let's look. If I look, that's what I get. Pretty close to a straight line, right? Okay, so we're going to go as it's normally distributed. Now, just because they say that, that does not mean we have to use t-score. Okay? So don't make the assumption if it's under 30, you have to use t-score. If it's under 30, we just have to check and make sure it's normally distributed. All right? Which means that we have to do that test. If they give me my population standard deviation, I still can do my z-score. Okay? So I basically need to know, do I know the population standard deviation for this problem? In this case, you do not. So we need to use T. That is the mean and standard deviation, so you don't have to go calculate it of the sample. Saves you a process of going and calculating it. So this one you have to use the T table for. And we're looking for, oh, sorry, I didn't tell you, 95%. Oh, shoot, hold on. That is not your normal standard. That is not your standard deviation. And I grabbed the wrong one. Because those numbers don't make any sense for this problem. That's your mean. Much better mean. And that's your standard deviation. Much better standard deviation. Yeah, those numbers didn't make any sense. All right, so what's our T score for this one?
1.7.
So we're looking at,
Oh wait, no. 75. Yeah, exactly.
yeah, yes. 2.110. Remember, we're looking at degrees of freedom of 17.
I was thinking from class problem.
Gotcha.
That next product, I already got it.
Right. So that's actually important. So like actually I'll look at this, I'll show you this real quick. So if you noticed, the 95% was 1.96 for the Z, right? As the degrees of freedom gets bigger and bigger, notice how that value is getting closer and closer to 1.96. So at the 30, which is what I told you is like the benchmark, you're at 2.04. You're only 0.08 off of the thing. So as the degrees of freedom is getting smaller, that number is getting further and bigger and bigger, which means my range gets bigger and bigger, right? So the more people you have, the more smaller, again, same thing we did with the Z, right? The more people that we have in the sample, the bigger the sample size, the more accurate my information is. Same concept here. As my degrees of freedom get smaller, my sample size gets smaller, therefore my range gets bigger. Okay? So we got 2.11 for this situation. So we throw those into Desmos. And we get our lower, upper, and our error. So I'm 95% confident that the mean for the average, the price, yes,
What decimal place do you want us to go to?
is one more than whatever the data they gave you is.
For this case, you want us to put-
Yeah, I just copy and pasted it from Desmos. So, yeah. So it'd be 1862 to 2067.4. So yeah, you always want to go one more decimal place than what they gave you. In this case, it's dollars. So if you went two places, it's fine. This is dollars and cents. But depending on what the data is, you typically want to go one more place because it's your significant digit. So, and my error is 102.7. That's what I'm going to be adding and subtracting. Okay. All right, so what's really the only difference between z-score and t-score? Yeah. If you don't know your standard deviation, that's it. Okay. I linked both of these. So you have your normal probability plot maker right there and your t-table. So they're both right there. Where your class notes and stuff will be after middle class. All right. Next week when we start chapter 9, it is probably the hardest chapter. Just because, so if we're thinking about it, like everything we've gone down so far, we've used other people's data. So it's like we really haven't, like we can figure out confidence intervals and stuff like that, but it's like we really haven't done any tests. When you're doing statistics, the goal is to be able to say, is your data accurate and does it say something about it? So we're looking at like the pandemic and stuff like that. It's like if we're looking at clusters, is the cluster in one place worse than anywhere else? We want to be able to determine that. Because if the cluster is worse in one place than somewhere else, it's like, okay, that means something else is going on there that's affecting it. Let's figure that part out. All right. Is it abnormal? That's what we're looking for. And that's what we're going to start looking at in chapter 9 is how can we start doing what's known as hypothesis testing? It's like, just like in science class, you take your hypothesis, then you have to test it. We're going to test it with data. So it's like, this is what I think's happening. Let's see if that's true or not. Okay, so that concept is what's tricky sometimes. It's a lot of calculations. It's nothing really crazy in terms of that. It's just trying to figure out, like, how do we determine if it's true or not? So that's the harder part. But that's in essence the true essence of statistics. That's the goal of it, is being able to have data and show if it's something's abnormal or it's fine. So that's what we're looking for. All right. So have a good weekend. I will see you on Tuesday. You too.